thanks for being here. We are Group 29, and today we are excited to present our machine learning final project. Our project focuses on a very interesting topic in computer vision, building a model that can determine whether a face belongs to JJ Lin, Lim Jun Jie or not. This problem may seem simple at first, but as we show later, distinguish between a target individual and look-alikes in real, unconstrained image is actually challenging and requires thoughtful design. Let's begin with the motivation behind this work. This is our content, and we just start by introducing problem and explain why we choose the topic. Okay, that's our background. As shown on this slide, face recognition is a very well-developed field, but our goal is slightly different. Instead of identifying many different identities, we focus on target space setting and deciding whether an image is JJ Lin or not. We chose JJ Lin because both team members are longtime fans, but also because he's a public figure with many available images, including concert, music videos, and social media posts. And this makes him a good candidate for studying recognition under real-world variations such as lighting, resolution, and facial pose. And list our research objective. The core objective of our study is to examine where machine learning models can reliably distinguish specific individuals from all others. Our problem is framed as a binary classification task, JJ Lin versus not JJ Lin. To understand model behavior better, we compare two different architectures: a fully connected neural network as a baseline and a convolutional neural network that can extract spatial and facial features. And this comparison allows us to observe how modeling spectral structure influence performance. To see our method overview and list size, first we collected images of JJ Lin and non-JJ Lin individuals from various public sources. And next we pre-processed the image, cropping face, resizing, normalizing, applying augmentation, and for the NN baseline using PCA for dimensionality reduction. We then trained two models for scratch using a neural network and a convolutional neural network. And finally, we evaluate both models on two independent datasets using accuracy, F1 scores, and confusion metrics. This is our dataset overview. Our dataset consists of around 7,000 images categorized into JJ Lin and non-JJ Lin, including many lookalikes. Because real-world online images vary significantly, preprocessing plays a crucial role. We applied face cropping to reduce background noise and keep the model focused on the facial features. We keep RGB images instead of converting them to grayscale because texture, color, and shadows often carry essential identity cues. And this step is especially important when dealing with visual similar faces. And in addition to face cropping and RGB preservation, we revised all images to 180 by 180 pixels and normalized pixel values. During training, we applied several augmentation strategies, such as flipping, small rotation, and bright light adjustment. And this helped improve generalization, especially because of our dataset comes from diverse sources with varying conditions. Okay, and because our two models operate differently, we prepared the data in two formats. For the neural network, images were flattened into about 97,000 dimensions and then reduced to 1024 dimensions using PCA, which retained about 95% of the variance. For the CNN, however, we preserve the full spatial structure and keep images in their original 180 plus 3 format, and this difference is critical as CNNs rely heavily on spatial relationship to extract meaningful patterns. Okay, that is our baseline model. Our first model is a fully connected neural network serving as a computationally efficient baseline. The input is the PCA reduced vector, and the architecture gradually reduces the dimension third layers of 512 and 256 units, and finally outputs a probability using the sigmoid activation. While NNs can capture global features, and they typically struggle to recognize local facial structure, and which is why we expect the CNN to perform better. Okay, the main model. Our CNN main model is designed to directly operate on RGB images. It has multiple convolutional blocks, and each containing two convolution layers followed by max pooling. As the number of channels increase from 32 to 64 to 128, the network gradually learns low-level textures, mid-level features like eyes and nose shapes, and higher-level facial configurations. After flattening the feature maps, the model uses dense layers and outputs a probability via a sigmoid function. This architecture allows the CNN to capture much richer facial details than the NN. Okay, the slides will show the proportional of classes in our two data sets. Okay, we intentionally keep the proportions consistent so that we could compare model performance fairly. Both datasets include a mix of JJ Lin image and look-alikes and non-JJ Lin individuals. This helps us evaluate how well the model generalizes beyond the training data. And list our results. Here we present our main results on dataset 1. The CNN achieved about 76% accuracy and an F1 score of 0.74, and while the NN achieved only around 41% accuracy and an F1 score of 0.4. And on dataset 2, the CNN obtains 57% accuracy and F1 score only 0.55, and again outperforming on the NN baseline. From the confusion matches, we can see the CNN is much better at identifying JJ Lin correctly, while the NN tends to classify many JJ Lin's images as non-JJ Lin. calculus are in limitations. Also, our results are promising several limitation exits. First, because our dataset was collected from public source, and the images differ greatly in quality, lighting, and pose. Some samples are low resolution or ambiguous, which increase the difficulty of classification. Second, due to the limit computational resource and no access to a GPU, we could not train deeper models and run extensive hyperparameter tuning. And these factors definitely influence our performance, I think. Okay, our method also have limitation like this. The neural networks reliance on PCA reduce details and many remove important identify specific features. And the CNN was trained from scratch and was not compared with pre-trained face recognition models, which might offer stronger baselines. Additionally, our group size was reduced to only 2 active members, so development time, experimentation, and optimization were relatively limited. Okay. Okay, so our conclusion. To conclude, our project explored the task of determining whether an image belongs to JJ Lin or not. Across both datasets, the CNN consistently outperformed the neural network baseline, demonstrating the clear advantage of leveraging spectral feature. And we also found that preserving RGB information is crucial for distinguishing visually similar face. And overall, the CNN offered more robust and stable performance, even in challenging real-world scenario. So to our future outlook, we hope to improve dataset quality by performing more systematic data curation. And with better computational resources, we would also like to conduct more extensive hyperparameter tuning. And another direction is to explore hybrid or more advanced architecture, or apply transfer learning using pre-trained face recognition models. So finally, the framework could be extended to support multi-identity classification rather than a single target. Okay, that's our final project. Thank you very much.